Okay, so now we want to look at the work done or energy and potential later on. First, the work. So if we have a field going into this direction, so this is a field. Let's just call it E. Then I have a point charge somewhere here at this point, which is just equal to Q. Then I want to move this charge into this direction, towards that direction. So to move that charge, I need energy to do that. And also, if you remember the definition of a work is just the dot product of the force and the displacement, how much displacement of forcing a certain mass or a charge movement in a certain displacement. So here, we will be needing also a force when we try to move this Q. And that force will be, of course, in the opposite direction. It's in this direction. That will be our F. That will be the force going into that direction. And if we try to solve for that force, remember Coulomb's law, the relationship between the electric field intensity and a force. Remember, E is just equal to force over Coulomb, Q, because the unit here is Newton per Coulomb. So E is just equal to, or force, that force is just equal to, let's just use weight here. That force is just equal to Q times E. Just multiply the electric field density with that Q. But here, because F is in the opposite direction of E, so we just need to put a negative sign to do that, because it means that the force is in the opposite direction of E. So this is the force. And just like what I said, work, a definition of work, is just the dot product between the force and the displacement. But what happens if the path of the charge that we move is not a straight line? It goes like that. So what will be that displacement? So normally what we do is we zoom in. We zoom in this path. And if we try to zoom that, eventually we will be having a straight line. Very small straight line. Just like a pixelated something. So if we zoom out this one, it looks like a curve. But if we zoom in, pixelated, these are straight line now. So if these are straight line, and that will be the straight line that we need to solve for the work moving this charge from this point. This is the part of that one that being zoomed in here. And this is, we move this charge, this will be Q. We move it into this point here. And that will be, what will be the work? So what will be the displacement? The displacement is this distance here, because this is very, very small. So we will call that our DL. So remember the definition of differential calculus. It's infinitesimal, or very, very small. So that's the concept of calculus. Because this is very, very small. We zoom in, because it's now a straight line. To do that, it's just a small part of that arc length, and that is just DL. And we'll also make this one as a vector, DL as a vector, and we did that in the previous chapters. And we already know what are the DL in Cartesian, or in cylindrical or spherical. So for in Cartesian, mostly DL is just equal to dx, the x direction, plus dy, the y direction, plus dz in the z direction. If you want it in cylindrical, then this is just equal to d raw in the raw direction plus r or raw d phi, the arc length. If we already derived this a phi then plus dz az, and for the spherical coordinates, this will be dr ar plus r d theta in the theta direction and plus r sine of theta d phi and e phi. So if you want to recall the derivation that we did from chapter 1, you can rewatch our lecture again, but this time I will not derive this again. So these are the DL that we will be using here, because this is a very small distance displacement, and the energy, because we are moving it in a very small displacement, so the energy that we also solve from that is also very small, and that's just dW. So we can just call it dW. So the energy that we need to move this Q here to this point to this point. And we have a force again that we are applying, and that is equal to F. And that's just equal to negative QE. Then if we solve for that dW, that very small energy, so how do we solve for the energy? Energy is the scalar product. Because energy is scalar quantity, it's the scalar product of the force that we applied and it's a dot product because it's scalar quantity, and the displacement, also a vector displacement. So F dot dl, that's the very small work that we did from moving Q to this point. So now to solve for the total energy, then you just need to take the integral from this point to this point. It depends on what point are we solving to solve for the total work done. And we actually did this also in chapter 1. We practiced doing this. So it will be an easy job for you already to solve them. So F is just equal to negative Q E. This is our F. Then take the dot product DL. So if I solve for the work, total work done from point A to point B, is just equal to negative Q, or we can just move that Q outside the integral sign because it's just a constant. The integral of E dot DL from A to B, from point A to point B. So this limit here depends on your DL. And we already know how to evaluate this. This is a line integral in chapter 1. Okay, so that's the work done. This is the work done moving a charge from this point to another point in an electric field. It's a dot product. And then if we take our example, our same example before, so let's take an example. So this example, it's a similar example that we did in chapter 1. At this time, knowing where the formula, this is not the formula, we derived the formula that I just gave you last chapter 1. Just give you this one. But now, because we're in this topic, so we already discussed where that formula came from. And we can apply that now and solve this problem. The solution. An electric field is given. This is the field. X over 2 plus 2y in x direction and x in y direction. V volts per meter. Find the work done in moving a point charge, which is equal to negative 20 microcoulomb. So letter A, from the origin to 400, from 400 to 420, then so on. So let's start with letter A. So we move the charge from the origin. So this is just a two-dimensional x and y, because from the origin is 0, 0. So we start here our Q and we move that to 4, 0. So this is x. This is in the x direction. So we move it 1, 2, 3, 4. And there's a field around this. Remember, there's a field around this, which is equal to this one, this field here, x and y direction. There's no z direction. So it's just in xy plane. So we're moving this charge from here to here. That's the motion and the movement. So we start at 0, 0, 0, and we want to move that into 4, 0, 0. And it's just a straight line, so we can just directly solve this one. And using the formula, so work will be equal to negative Q. Our Q is 20 microcoulombs, so this will be positive 20 micro. The integral of E, our E is equal to this one, x over 2 plus 2y ax plus 2x ay. This is our E, the electric field, and we take the dot product with dl. What will be our dl? So if you look at the path, dl is just one direction. It's just in x direction. So our dl here, dl is just equal to dx, ax. It's just in the x direction. So we just need to take the dot product of that with dl or dx ax. Dx ax. And if you take the dot product, you look at this, you can distribute that. Ax dot ax is just equal to 1, ay dot ax is just equal to 0. So we can just eliminate that part. So we just need to multiply it by dx multiplied by x over 2 plus 2y. So now, so this will be 20 micro, the integral of x over 2 plus 2y, then you multiply that with dx. Ax dot ax is 1, ay dot ax is 0, so this will be eliminated. Multiply it by 1. Then, what will be our limit? Our limit is because we're integrating with respect to x, and we start at the origin towards this point. So it will be from 0, that's the x value. Here, the x value is 4, so we just need to integrate from 0 to 4. But the problem is, we have y here. We need to remove this y before we integrate. How do we solve that y? What is the y value at this point here? And at this point. Our y here is 0, our y here is also 0. So this is just equal to 0. So we only have now x over 2 dx. And what's the integral of that? X over 2, or we can just remove that 1/2. What is the integral of x? It says x squared over 2. So you can use your calculator to solve this. So we can do that. So we have 20 exponent negative 6. So that's 20 microcoulomb. The integral of, we only have x over 2, so alpha x over 2 from 0 to 4. Press equals, and this will be equal to 8 times 10 to the negative 5, or we can rewrite that. We can make it 80 so that this will be negative 6 or micro. So W now will be equal to 80 microjoules. So the energy that we need to move that from the origin to 400 is just 80 microjoules. Now for letter B, so next letter B. So we move it from 400. So we start at 400. I can just use this figure again. So we start here and we move it at 420. So it's 420, 1, 2, 3, 4. Y is 2, 1, 2. So this is 420. So we need to move this 1 into that point. So that will be our motion. So this is 420. And let's solve that. So W will be equal to 20 micro. The integral of, you can just copy this one again. Paste it here. But this time, this DL will be different DL because we have length in the y direction. We have the length is just in the y direction. DL is going upward. So our DL for letter B will be just equal to dy ay. So this will be just dy ay. Why? Because we only have the y direction. It goes up, just going up, and that's the direction of ay. So it's just dy ay. So take that dy ay here. And we can take the dot product again. So this will be 20 micro, the integral of, so we have, this will become 0, ax dot ay. So the only thing that will be remaining is 2x. 2x dy. So we have 2x dy. And it's x. We are integrating with respect to y, but our equation is in terms of x. So we cannot do that. So we need to change this in terms of y. And what is our value of y into that point? So see here, or what's the value of x, because 2x. At this point, the value of x is 4. At this point, the value of x is also 4. So our x here is just equal to 4. So this one now will be 20 micro, the integral of 8, 2 times 4, 8 dy. And our limit should be from 0 to 2. So we just need to look at the y values because we are integrating in terms of dy. So the answer here will be, the work done will be just equal to 320 microjoules. Okay, so that's letter B. And for letter C, so this is different now. We start at 420 and we go back to 00. So this is the third path. So we start here at 420 and we go back here, going to that direction. This is the third path. This is letter C. This is letter A. This is letter B. And that's letter C. So for letter C, 420, go back to 00. What will be the work needed to do that? So I just need to copy this again. It's the same thing, but we only need to change our DL. We only need to change our DL. Why? Because this time, what will be our DL? So if you look at the path, we have two factors here. We have AX, and we have also in the X direction, we have in the Y direction. So our DL now will be just equal to, we have an X component, we have also a Y component. So this will be our DL, dx AX plus dy AY. And if you do the dot product, so this one times this one will be equal to 1. This one times this is equal to 0. So this one and this one is equal to 0. And this one is equal to, we just multiply that. So this will be 2 micro, the integral of x over 2 plus 2y. If you take that with the ax dx ax, that will be equal to 1. So you just need to multiply this with dx. And the other is 0. And for the y component, we just need to multiply the y component here because this is that product. Y and x components, the same components. 2x times this one. So 2x times dy. And we have two differentials here. So we need to choose what differential are we using. And to do that, first, we need to know the equation of this path. This is a straight line. And remember, how do we solve the equation of a line? One way of doing that is to use the slope-intercept form. What's the slope-intercept form? We have the slope and intercept. The intercept will be equal to 0. Why? Because it passes through the origin. The slope is just equal to rise. This is the rise. And the run, which is this one. Rise is just equal to 2. Run is just equal to 4. So m, this slope is just equal to the rise 2 and the run 4. So therefore, the equation of that line will be y equals 2 over 4x, or y equals 1/2 x, or x equals 2y. X equals 2y. So I just need to write it here. So if x equals 2y, we can solve for dx. I take the differential of x. So this will be 2 times dy, implicit. And we can substitute this here so that we only have one differential. Or you can solve for dy so that it will be in terms of dx. So you can do anything, or one of them. So it's up to you now. So you can just use dx. I remove dx and make it in terms of dy. So this will be, and also, because x equals 2y, if I remove dx, I retain dy, then I need also to change all x in terms of y. So in the first term, x over 2, we have x there, so we need to change that into y. Our x is equal to 2y, so 2y over 2 is just equal to y. Plus here, 2y. Multiply dx, already know that, that's just 2 dy. Plus 2x, again, x is 2y, so that will be y dy. And you can simplify further, so this will be 20 micro, the integral y plus 1 plus 2 is 3 times 2 is 6, 6y dy. And again, factor out that dy. Then we have 6y, and we have here plus y. 6y plus y is just equal to 7y. So 7y dy. There's a correction here. 2x, x is equal to 2y, so this will be 2 times 2y. It's not just y, it should be 4y. So this is 4y. We have 3 times 2, 6 plus 4. That will be, instead of 7, this should be 10 y dy. And the limit, because this is with respect to y, so we just look at the values of y. So we start at this point, the value of y is 2. We end up with this point, the value of y is 0. So this should be from 2 to 0. So from 2 to 0. So if we try to calculate that again, you can just use the calculator directly. So 20 exponent negative 6. Then the integral of 10 alpha x from 2 to 0. And the answer is negative 4 times 10 to the negative 4. So we make it micro, so we just add 2 zeros here, so 400. So the work done is just equal to negative 400 microjoule. You can also use the x if you want here. Okay, so that's the work done in moving a charge in a field. Now for the next topic, we will be looking at the electric potential. Electric potential between 2 points. Potential between 2 points in a field. Electric potential in a field. So if we remember in circuits 1, when I say potential, this is potential difference because this is 2 points. So when we say potential difference, that's voltage. That is voltage. And in circuits 1, what's the definition of voltage? What is voltage? Voltage is actually, that's the energy need to move a 1 coulomb of charge. So 1 volt is equivalent to energy you need. That's 1 joule to move a 1 coulomb of charge. So joule here is the unit for work, and C is the unit for coulomb is the unit for charge. So this is just work over charge. So voltage is actually equal to work over charge, or dW over dQ. Then, so if it's between 2 points, so for example, if I have a point charge here in the 3 dimension, so this is our point charge, Q, and I want to determine the potential difference between this point and this point. I can call this one point A, I can call this one point B. And if we assume we are in spherical coordinate system, so the distance here and that, we can call that vector R A, and the other one we can call it R B. And if it's a vector, it's in they are both in the AR direction. So A and B. So we want to determine the voltage between A and B. And we already know that's equal to W over Q. What is W and what is our Q? So our W, remember our W here, this one, it's just equal to, so equal to negative Q, the integral of E dot dl from A to B, from this point to this point, all over what? All over Q, because that's the formula here, W over Q. So this is W, and this is Q, so we can cancel that Q. So therefore, VAB will be just equal to negative of from A to B, E dot dl. So if you want to determine the voltage between that, it's just equal to this. And also, because this is the energy or the work is conservative for in electrostatic, we can say that if we have another point, a reference between A and B, let's say point C somewhere here. So if you remember in VAB, VAC will be just equal to, VAV will be just equal to VAC minus VBC. It's the voltage because it's conservative in circuits. Our circuits 2, we also did this one in 3-phase systems. And VAB we consider that as a potential difference. It's a voltage. So if we try to derive that formula now, we can try to do that. VAB equals negative, what will be our E? If this is a point charge, this is our point charge. This is our source of electric field, this E here. So remember, what is the E in a point charge? We already solved this. This is just equal to Q, not Q, all over 4 pi, if this is in this free space, epsilon naught, times R squared, then the direction is AR. This is point charge electric field. This is point charge, and we can use that here. So this will be the integral from A to B of that Q all over 4 pi epsilon naught R squared. Then we have dot, and the direction here is AR, and dot this one with DL. What will be our DL? So from here to here. So that's in the direction of R also. So this is just DR AR. DR AR. And AR dot AR is just equal to 1. And this will be equal now to A to B Q all over 4 pi epsilon naught R squared DR. And this part is constant, so we can just remove that. negative q all over 4 pi epsilon naught r, the integral from a to b of dr over r squared. And what's the integral of dr over r squared? The integral of dr over r squared is just equal to, so negative q, you just need to add 1 or minus 1. You put 2 r squared at the numerator, it will become negative 2. Then if you add 1, negative 2 plus 1 is negative 1. So you put that at the denominator, then it will become positive. This will become positive. Q over 4 pi epsilon naught. Then you multiply this with 1 all over r. And the limit is from a to b. The limit is from a to b, from this point to this point. So if we apply upper limit minus lower limit now, this will be negative q all over 4 pi epsilon naught 1 over r. So this will be 1 over the upper limit rb. This is rb here, the distance from point b and point A is ra, minus 1 over r b. And this is positive. Just make it VAB. So this will be the formula for VAB at 2 points A and B in a electric field. Now we can also make the other point if we are solving potential of a point charge. Just 1 point instead of 2 points. We can make the distance this distance here RB. If we take RB much greater than RE, if RB is much greater than RA, so if that is true, then we can treat RB as infinite. We can make that towards infinity, and we can solve for a simple voltage instead of VAB, just voltage V in general, and that will be equal to Q over 4 pi epsilon naught. And here we have RB. Here will go to infinity, so this will be 1 over infinity if we take the limit, or we can just make RA so that we can make this one positive. It's still the same. Instead of RB, let's say this is RA and this one is RB. Let's just interchange this. I'll make RA much greater than RB instead of RB much greater than RA. So if you do that, this will become 0, 1 over RA. And the only thing that will be remaining here will be 1 over RB. And if RB is just equal to R, then the formula will become just multiply by R. So this will be the electrostatic potential or electric potential. The unit here is volt V in a point charge. If you have a point charge, you want to determine the potential at any points distant from that Q, then you can solve that using that formula. And you can also do that instead of point charge. You can do that in terms of sheet, line, and also volume charge. The different configuration that we did in chapter 2, we can also use those. You can derive the electrostatic potential using those different configuration. And the method it's still the same. You just change E here, the value of E. Because for a point charge, your E is equal to this. But for a volume charge, your E will be different. And we already did that in a different configurations. So you just need to substitute dot E, and you can solve for the potential even in any configuration. Now let's take an example. A total charge of 40 over 3 nanocoulomb is uniformly distributed in the form of a circular disk of radius 2 meters. Find the potential due to this charge at a point on the axis 2 meters from the disk. So this one, we can put that disk in the because there's a disk, so we can put that into the xy plane. And the axis here, the point that we want to solve, we can make it in the z-axis. So for us to illustrate that, so if this is the xy plane, we can make the disk somewhere here at the xy plane. So if that is the disk with the radius of 2 meters, so the radius is 2 meters, then we want to determine the potential due to this charge at a point on the axis 2 meters from the disk. So if this is the disk, so 1, 2. So this is the point that we want to determine the potential. So now this is given. The total charge here is 40 over 3 nanocoulomb. That's a total charge. So because this is an area, this is a circular disk. So we can determine the density. This is a sheet charge, rho s, surface charge density. And you remember the surface charge density is equal to the ratio of the total charge divided by the area. The total charge is 40 over 3 nanocoulomb, and you divide that with the total area because this is a circle, and the circle, what's the circle? What's the area of a circle? It's just 2 pi r, or pi r squared. And our r is, the radius is 2. So it will be pi r squared. So r squared is 2 squared, 4. So 4 pi. The unit is, because that is in meter, so this will be in square meter. So that it will be in nanocoulomb per square meter. That's the surface charge density. And we can just cancel that. If I write this, I can make this 140 times 10 to the negative 9. Then over, I'll put the negative 3 or positive 3 at the denominator. So this will be, so this is 40 over 3, then 4 pi. Then you can cancel out that 4 here. So this will become 10. Or I can just make that 10 raised to negative 8 all over 3 pi. 10 raised to negative 8 all over 3 pi. This is coulomb per square meter. That's the surface charge. This is 0, 0, 2. This point here is also 2, 0, 0, 2 meters. Now, that's the charge density. So we need to solve the potential at this point here. So remember the formula for the potential equal to this. Or this one, we can use this formula here. Or because it's not 2 point, I can just use this. But the Q here and the R, what should be the R? The R should be, so if I take a small charge, dq somewhere here, the radius, let's say this is R, radius R. Then we have a vector that connects this point to that surface, small area. Just call that R, a vector. Then this angle here will be phi if it's in cylindrical coordinates. Now, what will be the magnitude of R? It will be this big R here. So it will be 1, 2, and R. So using Pythagorean theorem, R squared is equal to 2 squared plus small r squared. So R is equal to the square root of 4 r squared. This is in meter. That's the distance between the charge and this point. That will be our R. here, because our r here is actually the distance, remember, of the point to the charge. Then that's dq. I just need to change this with dq, and my r will be this one, and that will be my voltage v. So v will be equal to the integral, or dq. This is dv because this is a small dq here. So dq all over 4 pi epsilon naught. The distance will be equal to this r. You take the square of that, so 4 plus r squared. Okay. Next, to solve for v, you need to integrate this. So to integrate this, we need to change this dq. Our dq, remember, rho s. The rho s is equal to what? dq all over ds, surface area. So if I solve for dq, dq will be just equal to rho s times the surface area. And what is ds here? Our ds, remember this area here. So if we look at, okay, just recall that. So if we are in top view, so if this is the top view, I get a small, or I can just take the one here as area, then we have, this will be the area differential q, and this will be differential s. And we know this is just a square or a rectangle length times width. So this length here is just equal to this angle. This should be d phi. It's a small phi because this is phi here. So if that is d phi and this is r, this will be the arc length. It's just equal to r d phi. And for the other side, this one here, that's just equal to d r, because that's with respect to the radius. We already did this. So our ds now will be just equal to r dr d phi. So let's put that here. For our dq, you multiply that with the rho s, which is equal to this. So we can just remove that rho s and make it outside. So 30 over pi. Then you have ds, which is equal to this one. So r dr d phi all over 4 pi epsilon naught. Then you multiply this with 4 plus r squared. Oh, wait. The formula here should be just r. I forgot. So I don't need to square that. This should not be, should be still the square root of 4 plus r squared. So I just need to put the square root here. So the square root of 4 plus r squared. Then what's next? This is a double integral because we have two differentials, dr and d phi. And I already multiplied this here in 30 over pi, because rho s is just equal to this one, 10 raised to negative 8 over 3 pi. So if you multiply that with 4 pi epsilon naught, that will be equal to 30 over pi. So I can just remove that and move this here. Then what will be our limits? So we are integrating with respect to r and with respect to p. So for r, this is from 0 to 2. So we integrate from 0 to 2. So that's the limit for R. And for the angle dphi, it's 1 revolution. So it should be from 0 to 2 pi. And if you try to integrate this, the voltage, you can do this. We already did this one before. And the answer should be here. It should be 49. You can do that again on your own now. You can practice solving that. I'll just give you the answer for the voltage. It should be 49.7 volts. This is the potential at point 0 is 2. So you just need to evaluate this. R dr dphi 4 plus r squared from 0 to 2, 0 to 2 pi. So to do that, first you need to evaluate dphi. So for dphi, it will be 2 pi minus 0. So you just need to multiply this with 2 pi. And for r, you can apply because you have a square root here. Or you can let the square root of 4 plus r squared to be your u. You can do substitution here because you have r dr in the numerator. So you can do that on your own. You can also do that using your calculator, and you should arrive with a 49.7 volts. So that's the electrostatic potential, and the work potential. We also have another one here, the energy, but I will do that in the next lecture.